Good morning, everyone. Welcome back to my channel. My name is Marina. I'm lead instructor for maritime science at Maritime Open University and Maritime Training Center. And this is Celestial Navigation live lectures. We are continuing from this week, and today's lecture are going to be slightly different. They're going to be slightly different. I'm going to show you what we're going to do today. So let me switch to another scene. So today what I have in schedule is, as you can see here on the screen, I'm working on finishing the new new textbook for, let's go back to the beginning, to the first page. So this is practical textbook for mariners. Now it doesn't have a lot of pages here because I usually like to work on my books in Excel. I don't like to make my books in Word. And one of the reasons why I prefer to make books in Excel is because of this. So this common problem between decimal point and decimal comma. When I'm working on a textbook in Word, that means I have to make one book, completely finish it and with a point, and then for people living in different countries using different decimal separator, I have to change every point into comma for another book. When I'm working in Excel, that is much easier because I make the calculations the way they are, and then if I want to change from point to comma, I just change the setting in Excel, so he automatically not identifies a number that is 1.2 as 1,2 once I switch from UK to Croatia or German standard. But for the purpose of this video, I'm going to work it in the Word file. So far I have chart work, crossing TSS finished. So this is how to cross TSS explanation with step by step. And then I had tide tables calculation. Once again, you see I already made a mistake here. Everything is in comma, so I have to change that to point later on. But today we are doing celestial navigation, and we will start with the known star. And the way this is going to work is I'm going to type the explanation for you and for the future mariners that will be using this textbook. And as I type here, I will also explain to you what is that we need to do in order to calculate something if the object we observed is known star, and we also have known planet, sun at any moment, sun at noon, sun in the moment of sunrise and sunset, observing Polaris, what to do in case the object we observed is unknown, and how to plot that on the white chart. And as I type here the explanation, once everything is finished, so for example for the known star, I'm going to use your feedback to tell me, is that enough? Do you want me to write something more? And the end goal is for this document to be 100% efficient for the person who might not have opportunity to join the live lectures or not have opportunity to watch live lectures in the future. So the only resource that person is going to have is this textbook. So the first thing, if you want to make some comments, if you want to ask some questions as I create this document, you are free to ask. So let's start. So the first thing is, when we have a known star, we also know the date. So let's say observer is observing known star, and we need to know the name of the star. So let's say for the purpose of this document, the name of the star is Alliot. So that is one of the navigational stars, and the date is and now this is, I don't know how you write dates, but in Europe we go day, month, year. So if this is not the way you do it, so you can interchange that, but I will also type here so everybody knows day, month, year. So day, month, year at assumed position. So this could be also at assumed position. This could also be dr position. So dr position or assumed position is a position we obtain mathematically. So that means we are traveling in a certain course for a certain amount of time with a certain speed. And the end result is our assumed position. That could be our true position in case there is no current, there's no wind, there is no drift, there is nothing influencing us except our engines and our propeller and rudder. But if there is any kind of influence, this assumed position is not going to be our true position because of the wind and drift and everything. So this is our assumed position, and the end goal of any navigation, celestial or terrestrial, is to obtain our true position, our real position. So our assumed position is, and I'm going to split it, is latitude. Now, because the course is usually attended by Croatian and foreigners, I need to find where is phi. Let's see, can I find it quickly? If I cannot find it quickly, it should be under Times New Roman. Times New Roman. Greek letters, yes, I need Greek letters, and I need Greek letter phi. So latitude is also expressed with the Greek letter phi. I'm not in the Times New Roman, so that's why it's not giving me Times New Roman, and I need Greek. Alpha, beta, gamma, delta, epsilon, zeta, iota. Where is it? Phi. Come on, phi. I'm looking at it and I do not see it. Alpha, beta. Oh, here we have alpha, beta, gamma, delta, epsilon, zeta, iota. Where is phi? Here. This is phi. Okay. So if you notice this mark here in the papers or books, this is a mark that is used for latitude. So this is a short abbreviation for latitude. And latitude is a coordinate that tells us how far we are from the equator. And we are 25 degrees, 39 points. I need to make a point here, 0.2 minutes north. And longitude, and the sign for longitude, I should have it here, is lambda, Greek letter lambda. And it's 0.72 degrees, 56 exactly, minute west. Now, the reason why I placed 0 in front of 72 for longitude and I didn't put 0 in front of latitude, because latitude can only go between 0 and 90, 0 being the equator and 90 is either north or south pole. For longitude, longitude can have 3 digits. It can be from 0 to 180 degrees, so that means it can be 0 to 180 east or 0 to 180 degrees west. So that's why we need to emphasize the 3 digits of the longitude. So if it's 72, we plot it at 0.72. It is the same with course and bearing. So if the bearing is 67, we write it down as 0.67 in order to avoid confusion, so somebody doesn't add 1 or 2 in front of the 2-digit value. So that is our assumed position, or dr position. The next information that we need to know is if we are using ship's chronometer. So ship's chronometer, and did I misspell it? No. So ship's chronometer error, so ER. This is the error that is calculated. Let's see, do I have an image? Chronometer, ship's chronometer, let's put it here. So this is copy image. Let's see. Okay, so this is ship's chronometer. So let's put it ship's chronometer. So this is a precise clock that we have on ship. It's usually installed in the box in the desk of the ship, and it's also mounted on the gyroscope, not gyro compass, gyroscope. Gyro is allowing the stability of the chronometer, so it doesn't tilt in the same direction ship is tilting, so it's neutralizing the tilt, so it always stays in the same position, and that is reducing the problems with mechanism inside the chronometer. Of course, today we have electronic chronometers as well, but on some older ships you will have this as well. And now the chronometer error is the actual error between this clock and the time that is in Greenwich observation station. So Greenwich observation station is publishing today through the satellite, but in old days and still today through MF radio, the frequency beep at exactly noon. So you have 10 beeps, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then number 10 is the actual 12:00:00 of UT Greenwich meridian time, not time zone of Greenwich area, but exactly the moment of 12:00:00 per Greenwich time on Greenwich meridian for humans, not astronomical noon, but human noon. And at that moment, let me see, can I find the image of the logbook? Chronometer logbook. Chronometer logbook. Oh, I have, and I have a nice one. I have a nice one. Copy image. Let's put it here on the side. Come on. So this is, so let me put this in tables. So let's do this. Let's put you here. Let's put you here. Ship's chronometer is going to go here and center. And this is chronometer logbook. So what you actually do as a seafarer is that, thank you, Addict. Thank you, Addict. I know something about electricity as well. don't hold plus and minus at the same time with both hands. Thank you so much for the support. Thank you very much. Okay, let's remove the border, because we don't want to look at the border. So basically what the seafarer is doing, there is something that is called noon report, and that is done especially on bigger merchant ships. Every noon you actually check the sun at the moment of noon, that is sun at meridian. That is something that we're going to do later on. That is now our subject number 4. And that at that moment he checks either through satellite or MF radio if there's a signal. So he has a stopwatch, and basically what he's doing, he's looking at the chronometer. So he's looking physically at this clock, his clock, and he's observing when this clock is going to show 12 o'clock. If the signal on the satellite or on the radio frequency is still not 12, so he's still not hearing the 12 beep, but the clock is already at 12, so he starts the stopwatch at the moment chronometer is showing 12, and then time continues, and then he waits for that 10 beep from the satellite that is going to indicate exactly 12:00:00 at UT, and then stops the stopwatch. And that is chronometer error. So the error can be either positive or negative. So our ship's clock can be slower or faster than the actual time. So in our case, in this task, it's negative. So negative 00:01 minute and 39 seconds. So if, and this is how we write time usually. So this is how we write angles and so degrees and minutes. And this is chronometer error time. So 00:01:39. Now the next thing that is important to know is height of eye of observer. Now height of eye of observer is important, and it's expressed as HIEA, that is the abbreviation that we use, is because all the data that we have in Almanac, everything that is written in Almanac is for chart datum or water level. If you are not observing something on your horizon from the water level, that creates something that is called depression of horizon, and it creates additional correction you must apply for everything that you measure, that is called dip. So that is why we need to know height of the eye of observer. That is how high we are from the water level. The way you would know this on your ship is by knowing the draft. So in your data of your ship or your yacht, you will have the total height of your vessel, or you will have the height of your deck. Where is your main deck? And let's say your deck is 10 meters. So that's the height. That is from the bottom of the keel, the lowest portion of your vessel, up to your location, so 10 meters. So if you have your gauge that is showing you your draft, and let's say your draft is 6 meters, so your ship is 6 meters in water and your total height is 10, that means that the height of your eye is 4 meters. So 10 minus your draft, 6 meters is 4, height of your eye is 4 meters. But for this is 16, for this task is 16 meters. Next important thing is that we are using, let's see, do I have an image? Let's hope I can find one that I actually have in my office. No, it's not that one. Astra, I believe mine is Astra. Yes, mine is Astra. This is mine. Let's put it here. Now this is, I need to, okay, I will do this later. I will reduce this image because it has too much white space around. So this is Marine Sextant, and this is a device that is used to measure angles. Now people say this is device for celestial navigation to measure height of the object above the horizon, but that is correct, but 50% correct. This is a tool that can be used to measure angles, and the angles can be anything. It can be vertical, it can be level. So you have 3 dimensions. It's a tool to measure something. So if you are holding it straight forward, you will measure vertical angle. If you are holding it flat in your hand, so you turn it by 90 degrees, you will measure horizontal angle. So it is an angle measuring device. So it doesn't have to be used only exclusively in celestial navigation. It can also be used in terrestrial navigation. I do have one video that is covering horizontal angle method. It's on Croatian language, but soon I will record the English version of that video as well. So this sextant, when it's produced, it can have an error that is permanent, that cannot be fixed. Usually there are tiny errors here with this mirror or with this mirror, but you have tiny screws on the side that you can use to adjust if there is some movement, if there was some distortion with the sextant itself. But there are some errors that cannot be fixed, that are permanent, and usually they are on the label of the box and also in the label inside the box, and they belong to this individual product. They are not like for entire series the same. So every sextant, after it's been produced, it needs to go to manual checkup, and that manual checkup actually logs the error of that unique sextant. So it's not like, okay, you can take the log book of correction for one sextant and then use it for another sextant. It doesn't work like that. So it's each sextant has its own unique errors, or it doesn't have errors. It depends on the way it was manufactured, and of course it's just standard in industry that there could be some deviations. So index error of sextant. Now it is usually labeled with letter E, but as same as everything in this planet, on this planet, everybody has their own mark. So I'm going to just put it like error E or index error, or I'm going to change this later on. I'm going to look There is a book that is called Bowditch. I don't have the print version, I only have electronical version that can also be purchased, and it's one of the first books that has everything for navigation. And I'm going to check what they are using for index error abbreviation, so I keep everything universal, so I don't make up my own, because that is what I hate, when people make up their own labels for something that is 300 years old and it already has its fixed label. So for the purpose right now, because I don't want to waste your time, I'm just going to call it error I, index error, but later on in the document I will change that to the official label of the index error. But the index error for this device is negative 0.2, and is it a point? Is 0.2 minutes. So that means every value that we measure with this sextant at this angle is minus 0.2. So whatever we measure, we need to subtract negative 0.2 minutes in order to have corrected value. What else? What else? We have temperature, air temperature. How do you spell air temperature? So that will be temp. That one is easy. Air temperature is 16 degrees Celsius, and air pressure, sure, that will be press. That would be 980 HPA, hectopascals. And I will remove later on the white of this image so everything fits on one page. Also, I can shrink this as well. It doesn't have to be this big. Okay. Later on I will, don't worry, sorry, later on I will do the visual correction of everything. And now what we have is we used this device, and the moment, so time of observation is TCH, so that's chronometer time, and chronometer time is 23:58:45. We do not use AM PM here in celestial navigation. We go from 0 to 24. So 23:58:45, that's time of observation, chronometer time, and the height observed with sextant. When you see my typos, that is because I like to cheat, because I actually paid for professional grammar, spelling, auto fixing software. So I just type what I have in my brain and then the computer corrects my grammar. I was a straight A student in everything except grammar, so I'm not proud of that, but I'm also not ashamed of that, because my core is mathematics. I'm not here to type novels. So let's move on. Height observed with sextant is 30 degrees. So this is the height I actually measured with this device, and it's 30 degrees 17.9 minutes. So that is how high the star Alliot I observed is from my eye horizon, not the actual sea horizon, because I didn't jump in water. I'm actually on my ship, on my yacht, observing this star. I did that at 23:58:45. That is the time I recorded from this device. And from the sextant, I have height observed with sextant 30 degrees 17.9. And now, on to the first step. So this is what I have. This is everything I have in one task, and this is the task for the known star. This term here, known star, means that we will have also option that we observed object that is unknown. Basically everything will be given except this information here. So we will not have the name of the star. So let's start with step number 1. Now what I like to do is I like to label my steps. Let's see, can I find them quickly? I have a special font I use, yes, number pile, yes, step number 1, insert, close. So I like to label all my steps, so if student has a problem with a certain step, he can write me, okay, Marina, can you please help me? I have a problem with step number 3 on page that and that. It's much easier for me to assist students when they can tell me the exact step they have a problem with. Otherwise it will be, can you help me, what's the problem? Sun deviation. And sun deviation is 3 pages of the task. So step number 1 is correct UT time, and the correct is not spelled like that for sure. So first step before we correct time, and don't forget and date, very important, and date. Let's put explanation mark x or something, this mark here. So correct UT time and date. Why am I emphasizing the date? Sometimes when you are observing, this clock is showing you Greenwich time, but you are somewhere else. For example, you are 72 degrees west. So that means the time that you are observing, is not 31st of August, it could be a different date. So this is my local date. This is this number here. This number, I didn't take it from here because as you can see here, there's no date here anywhere. There's no date. This is just a clock. Doesn't have a date here, doesn't have a calendar. So I'm looking at this, and I'm looking at my wall where I have a calendar. And the calendar is obviously for my local position. So my local position is 31st of August, but my time here is UT time. So that if I cross midnight, if this device crosses midnight and I'm west, that means this device is in tomorrow while I'm in yesterday. So I need to make sure that if I'm using the time, I also have the correct date that belongs to this time, not to me where I am, because everything needs to be converted to Greenwich. Okay, let's continue. So first is correct UT time and date, and let's create a table that will have, let's say, 4, and I can add more later on. So TCH, and you're going to capitalize that, and I don't want you capitalized, so undo. Time chronometer plus error will give me UT. So the time I read from chronometer, if I add to that time, if I add error of that device, I will get UT time. So let's shrink this a little bit, increase this a little bit so I can type. Let's remove, and let's put this here. Okay, so let's type in the time. So the time of observation was 23:58:45, and the error is minus, so I can copy this hopefully, so I don't have to type it in, past, and let's align this so it's looking nice. Okay, and let's bring calculator on, and we will use calculator because calculator can calculate this. Of course you can do this by head if you trust yourself, if you are proficient in mathematics. So I have a time minus, because plus and minus is minus, so 0 hours 1 minute and 39 seconds, and that makes the time, and the result is 23:57:06. So that is my correct. What happened to you? I didn't. Okay, perfect. So this is the exact time, UT time of observation. And now let's check the date. Is the date still the same? So I'm observing on 31st of August. I'm 72 degrees west, so 72 degrees west, west is negative. and let's divide that by 15. So that means 5 hours. That's 5 hours minus. So my time is 23 something plus this one. So I have 6 p.m. So when I was observing Elliot, it was sunset at 6 p.m. on 31st of August, and at that moment when I was observing Elliot, it was 6 p.m. for me, so 18 for me, but for Greenwich it was still 31st of August, just around midnight, so 23. So when I have 6 p.m., Greenwich has 11 p.m. So that's logical because I'm on 72 degrees west. But it's a good thing because we are still on the same date, so 31st of August. I sincerely hope I didn't make mistake with the name of the month. Is 8 August? Somebody confirm, blink twice. So the date is 31/08/2008. So that's the time and the date. So correct UT time and date. So after we have, let's go to insert symbol, more symbols, number 2, insert. So step number 2 is find the correct date page in Almanac. Find the correct date page in Almanac. So after we have corrected the chronometer time with chronometer error, we have UT time. We need to make sure that the date is still the same, or if we cross midnight, we have 1 day plus, so it will be first, but it's not, so we are still in the same date. So find the correct date page in Almanac. So this is the moment where you actually open your Almanac and you look for the date. So the first thing is look for the date. So let's find the date, and let's screenshot this. Like this. Okay. Come on. Next page. Okay. So you flip the pages until you find on the top you find your exact date. And for us is 31st of August. And once we have the correct date, we also have two options. If you've seen my video from Monday, and also, let me see, can I show you this? Can I bring this up in the system? Blah, 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 blah. Let's see. No, it's not on. Let's go back to this one. I have to, what do I have to do to show you the, I have to go on Samsung. Give me a moment. When I say to my colleagues that I have 3 monitors, they tell me that's too much, and I say that's too little. I need more monitors. I need 6. Okay, so this is the Almanac that I'm using for this textbook. It has worldwide shipping. You can purchase it here. It's not available in bookstores because all my books are made exclusively for each individual person that is ordering, because some of my books are unique. So if the person A purchased this book and the person B purchased that book, they do not get the same book. They get the same concept of the book, but they have different calculations, different numbers, but this one is available for everybody. So it's Nautical Almanac for Education, and this is the one I'm using. So basically you will have this book, you will open it, and once you open it, you will have 2 pages. One page will be on the left side, the other page is on the right side. So technically when you open it anywhere, in the middle or whatever, the entire section is called one page, not the numerical page, but everything that you see in front of you is called, this is how it is done in maritime industry, it's called one page. Then you have the left side of that page and the right side of the page. The left side is usually reserved for planets and stars, and the right side is for sun and moon. So when you are using star, in our case we are watching star, that means we are actually using, let's go back to this one, we are actually using the left side, and this is the left side, the left page for this date. And here we have the data for Aries, that's the spring point, that is sun frozen, virtually frozen in a position of spring, because we are taking advantage of that position, because as you can see here you have GHA deck, GHA deck, GHA deck, and then for Aries only GHA. So that is Greenwich hour angle. How far is the spring point from Greenwich? We do not have deck, and the reason why we do not have deck, because deck is a term used for declination. That is how far something is from the celestial equator. Spring point and autumn point for Earth and Sun, when it comes to their position, individual positions to one another, is when the Sun is exactly on the extension of the level of the equator. So exactly on the equator. So throughout the year, Sun goes 0, then you have summer, and then goes back to 0, and then you have winter. So summer and winter are maximum, while autumn and spring are actually 0. That is the moment where sun crosses, virtually, not actually, but crosses the equator. And because of that, we are using that advantage, because if declination is 0, then when you have those long formulas, a lot of things in those formulas get cancels out, because sine and cosine of 0 is either 0 or 1. So it makes calculations easy. So that's why we picked Aries, and that is why we have it in the book, in the Almanac. So find the correct date and page in Almanac. So first we need to look, and let's input here. So step 1 would be this. Let me change fill. Come on, more fill options, transparency. Okay, maybe different color. Let's see, red. Okay, red, and let's move no outline. So that would be first step. So that would be step number 1. So red is step number 1. Find the correct date pages. Every page has 3 dates. So every page has 1, 2, 3 blocks, and for every full hour between midnight to 23, midnight belongs to the next day, you will have on the one page, you will have 3 dates, and we are looking for 31st of August, and let me just copy this here, and let's zoom this in a little bit. And this is going to be, we already had a red, so let's go with, I don't know, maybe purple, and this, then this can be green. This will be green. Let's go green. Okay. Let's go back to black. So with full hour, so from our UT time, so that's 23 in our case, 23, we read the value of Greenwich hour angle of Aries. The reason why we are reading Aries is because we do not get Greenwich hour angle of star. That is not given to us in Almanac. And the way we get Greenwich hour angle of star is that sidereal hour angle, this SHA here that you see on the top of the list for the star, is the actual value between star and spring point. So in order to get Greenwich hour angle of a star, we need to take this number and add the distance of the star to that number to get Greenwich hour angle of the star. So the first step is with full hour from UT time, 23 in our case, we read the value of Greenwich hour angle of Aries. So let me get purple box shape, and I'm looking for 23. So 23 is here. Let's make it purple and let's make it transparent. Completely almost. Okay. So 23. So Greenwich hour angle, GHA of Aries, and now we go back to Greek. Do I have gamma? Come on, gamma. So Greek letter gamma is times New Roman times New Roman. Greek, let's find Greek letters. Greek letter gamma, alpha, beta, gamma, delta. So it should be alpha, beta, gamma here. So Greek letter gamma is used as an index mark for Aries. So this is a mark for Aries. So Greenwich hour angle of Aries is 325 degrees, 29.4 minutes. So this is how we obtain Greenwich hour angle of Aries. And also while we are here on the same page, we can read out the data or info for the star. Now this is something that you do not have to do it like this, but this is something that will help you save time, because we have this page and a certain amount of data is read from this page, but it's not going to be used in the same order. So I will read this value, this value, this value. Right now I need this value. I do not need this at the moment. I will need this later on, and I do not need this right now. I will need that later on. But while I'm on this page, I can take the advantage of me being on this page, make a note of the important data from this page, so I don't have to go back later on this page. And from this page, I can also read SHA of the star. And do I have, come on, that's in the star. Oh, I have star, yes, perfect. Close. So SHA of the star, so we enter this side here with the name of the star. The name of the star is Alliot, so it's on the beginning because the stars are alphabetically ordered. So I need one more color. What's that going to be? Let's put that in orange. Let's put that in orange, and let's set the transparency once again. Okay, and now let's look for Alliot. Where is Alliot? Here it is at the beginning. Okay, come on, shrink. Perfect. So SHA of Alliot is 166 degrees 24 minutes, and declination that I do not need right now, I will need it later, but because I want to save time, I will write it down. Declination is 55 degrees 54.9 minutes north. This is very important to note. Is it north or south? In our case it's north, so that is something that we need to note. So 325 29.4, 166 degrees 24 minutes is sidereal hour angle. Declination is 55 degrees 54.9 north, and that's it. That's everything that we need from this page. There is nothing here that we need. We don't need to go back to this page if we actually may correct date, correct hour, and correct data from the star. Okay, so we have the purple and we have the data for the star. Now we need to fix the green part, because this value here is exactly at 23:00:00. The Earth is going to move by 57 minutes and 6 seconds by a certain amount of degree. Now, sometimes people say, okay, if it's 23:57, why I cannot just take midnight and round the number? That is not how we work in celestial navigation. Celestial navigation needs to be precise, so that means we take the full hour. Even if it's 23:59:59, we take 23, so we go step by step, 23, and then for these two numbers we actually look into the table of corrections. What is this? 2 hours. So red, find the correct date, so that is in red, and also orange. So later on I will decorate this to look nicer. So red, and this is purple. So I will make the aesthetics later for this one. Now let's put a page break and continue here. Now what we need is the green part, so let's do this again, copy with the same parameters. Now for the green we have something that is called increments and correction tables. Increments and correction tables are part of every almanac, and they are the part that is not changing every year, so it's the same. So no matter what almanac you have, no matter what's the year, you can use that section for any calculation of any task in the future or in the past. The only thing that is changing in every publication of Nautical Almanac is the data belonging to that year when the almanac was printed. Now, this can create problem, especially in education, because Nautical Almanac is constantly changing. It's every year new. So if you prepare your, and I'm talking this as instructor towards other instructors, if you prepare your textbook for, let's say, Almanac that is 2008 or 2010, now you can also have that Almanac couple of copies, but you cannot purchase. Usually hydrostatic institutes, they do not publish, they do not print almanacs for previous years. You can only purchase almanac for the current year. You cannot purchase for previous. There are some copies available that you can find, but usually you cannot find them in the amount that you would need for the classroom, like for 20 or 30 students. And that is one of the reasons why when I was developing this almanac, my focus was to have something that is constantly going to be available. It doesn't have a year, as you can see here. It doesn't have a mention of a year anywhere. So basically, the purpose of this Nautical Almanac for education is that you as instructor or you as a student can buy it. It's available always, and you will have textbook. I'm also working on a textbook that will be a part of the series for celestial navigation. And also you can make your own task, and you can have a textbook with the task and numbers connected to this almanac for education, and it can be valid this year, next year, 10 years, 30 years in the future. Your students will be able to buy the educational Nautical Almanac and use it for practice, because basically what you need is almanac for practice for students. You do not need the actual almanac of the current year, because they are not sailing. They are not using the values obtained from the almanac for sailing. If you are on a ship, if you are on a yacht, and you want to actually calculate valid data, then you need to have almanac that is for the current year when you are doing the calculations. Okay, so let's go back to the Word file. Okay, so 23:57:06. So we have increments and corrections. So let me just find the minute. Increment and correction. corrections. Tablice korekcja, table of corrections. Did I open? I didn't open that file, so I need to search for it. Let's search it together. I'm going to open it. Let me show you the file I'm looking. Nitro, yes, okay. So I'm going to pull up increments and corrections. Give me a moment. Celestial navigation, Almanac, increments and corrections. Increments and corrections. Okay, so this is, let's zoom in. Increments and corrections from Nautical Almanac. So every page has 2 minutes. Every minute has 2 separated tables. In my almanac, they are physically separated. In this copy of the almanac, they are separated by these 2 lines in the middle. Now we are looking for, where is the value? Where's my mouse? Sorry, my mouse disappeared. It's hiding from me. Let's see what's happening here. So we are looking for 57. So 50 is, oh, that's on the bottom. Let's go on the back. 58, 57, 06. So let me, come on, move. Let me zoom this in. 06. Let's take a screenshot of this. Increments and corrections. Okay. And let's put that in Word. And let's go back. Let me take you back to the Word file. Okay, we are back in the Word file. So, the green. I don't want you green. I need you to be black. Later on, I will fix the color. So green. In table, how are we going to increments and corrections table? We look for minute 57, and under Aries column 0.6 seconds value. Okay, so let's use, we are on another page, so the color doesn't matter. So 6 here, shape fill, shape transparency. Okie dokie. So for 57 minutes and 6 seconds, Earth rotated by 14 degrees, 18.8 minutes for spring point, Earth spring point. So 57 minutes and 0, 1, 2, 3, 4, 5, 6 seconds. So we have all 60 seconds on the side. The first column is for sun and planets. So in case we observed sun or planet at this same time, the correction would be this. In case of star, we are using spring point, so we are looking at the second column, and the last column is for the moon. In case we observe the moon, we would use this data here. So now that we have all of this, let's put everything in a nice form. Let's do it like this. So first we have, let me copy paste that, we have Greenwich hour angle of Aries. So that's the first thing that we have, Greenwich hour angle of Aries. Then we have plus correction for minutes and seconds. And as a result of that, we have, once again, we have Greenwich hour angle for the exact time. So this is for 23. This is correction for 57.06, and this is the exact Greenwich hour angle at the moment of observation. Then we have longitude. Our longitude is, let's do this, let's select everything, let's shrink this here, and let's make no border, so this one is first, this one is second. So after we add on our Greenwich hour angle, that is how far the spring point is from Greenwich at 23:57:06. After we add our longitude, what we're going to get is, let me copy this, copy, paste here. We're going to get local hour angle. So this is how far that point of spring is from our meridian, because this is the distance. So this is the distance. GHA is the distance of spring point from Greenwich, and longitude is distance of my position or position of the observer from Greenwich. So these two, when you add them up, it will give us local hour angle. That is how far my meridian is from the approximate meridian of spring point Aries. And that will give me local hour angle. And do I have more lines here? Just to be safe, I'm going to insert below. No borders. So this is how far the spring point is from me, and I need to add, where do I have star? Yes, this is what I need. If I add this to that value, so plus sidereal hour angle of the star, I will have, come on, no, not like that, undo, I need a star, yes, I will get local hour angle of the star. So that is how, this is how, this now value is how much the spring point is away from me, and this is how much the star is actually away from me, because this is how much the star is from the spring point. Now the reason I use this order is because this order, if you apply this order all the time, you can also use it in case you have an unknown object. So the same calculation will be for an unknown object. The only thing that you would skip is these two parts, because if you have unknown object, you will not have these values. You will not have SHA of the object in order to get local hour angle for that object. So that is why I'm using this pattern here. But this is the school way. So this is the school way. Let's copy this. Copy. This is the school way. The actual way to do this is by keeping everything simple. So delete row. And what else? I don't need this one as well. Delete row. And let's change this one, no border, and only this one. So basically in high school, in maritime college, in order to get more points, you need this sum result, this sum result, and the final result. But in the actual navigation, we do not need those numbers because we are not going to utilize them anywhere. So you have this plus this plus this plus this, and the end result is what we need. So let's type this in. Greenwich hour angle was this value here. So 325. Correction we obtained was 14. What is it? Oh, I'm looking. Why are you 60? Oh, 12. Come on. So the correction for not you, go back and let's shrink it, and let's layout insert right. Yeah, that's what I need. Our longitude is, let's go back to the beginning of the task, and this is our longitude. Keep in mind it says west here, so it's west, and here in the equation when I'm calculating, if I want to emphasize this value is negative, what I do is I put negative sign, and that is how calculator knows, come on, that is how calculator knows the value is negative or the value is west, by putting the sign negative. And sidereal hour angle of Alliot was this one. Copy. Let's go back here. And now we take calculator. You have the calculator on. Let's start with 3 to 5 degrees, 29.4 plus 14 degrees, 18.8 minutes, minus 72 degrees, 56 minutes, and plus 166 degrees, 24 minutes equals, and we get, and I'm going to write it down, I know it's not correct, but I'm going to write it down, 16.2 minutes. Let's split this, let's put this 0 so everything is correct. Now make a note, LHA is measured in 0 to 360, is measured in 0 to 360 of what? And how to express this? LHA is measured in an arc, that is the term, in an arc of 0 to 360, and it cannot be less than 0, so that means negative, it cannot be negative, or greater than 360 degrees. What is this mark? 360 degrees. So LHA is measured in an arc of 0 to 360 degrees, cannot, I'm missing a comma here, cannot be less than 0, negative, or greater than 360. So in our case, we got it over 360. So let's put another column down below. Let's remove the border for this one. So LHA, copy here, and let's put this in red, and let's put the warning also in not what's going to look, this looks horrible, LHA, so minus 360. So this value that we got, minus 360 degrees, because if you get this, if your calculator is showing this, if it's returning you the answer like this, all you have to do is press this button here that is directly above the delete button. But you can also cancel this. So let me just write this down. 73 degrees, 16.2 minutes. And now I'm going to show you on calculator how to turn this off. No matter what calculator you have, I know I'm using Casio here, but no matter what calculator you have, the distribution of buttons and their function is the same. So you need to press the upper left button. It's either a shift or second function, and then mode, and that will show you this on screen. So you have 1 math and 2 linear. So we're going to choose 1 math. We need to keep the math because we want to be able to use this button here. If you press 2, you will not be able to use this button here. So that's why we want to keep the math as math. But boy, it's not giving me. Let me see. Okay. This is older version. Sorry, this is older version of calculator. I will have to find a newer one. So what will happen here? Once you press shift and mode, shift and mode, it will give you, sorry. Sorry. It will give you, you will press 1, and then it will ask you how do you want the results to display. Do you want them in math or linear? And then you select linear, because math is going to give you this. So 2 divided by 3, it's going to give you this as a result. And then you have to convert it to number by squeezing this number here, this button here, sorry. But if you press shift mode number 1 and then number 2, you will be able to use this button here for up and down, but the result is going to be displayed, not for me, as you can see, the result will be displayed like this. So that is how you fix this issue on your calculator. If you cannot fix this issue on your calculator, if you have problems with that one, send me the picture of your calculator switched on, and I'm going to send you the steps of instructions on how to do that, how to fix that. So this is where are we? This was step number 2. So this was all 2. This is then step number, do I have insert page break, and this was step number 3. More symbols. Numeroc, where's numeroc? Come on, number pile, step number 3. So step number 3 is calculate local hour angle of star. So that's step number 3, and that is what we did here. So step number 3 would be to calculate local hour angle of the star. We have Greenwich hour angle that we read from the Almanac using the UT hour. We have correction with minutes and seconds. We have longitude of assumed position that is given to us in the Almanac. That is given to us in the task, sorry. And we have sidereal hour angle of the star that we read from the Almanac. Once we summarize all this, if we get number that is under 0 or over 360, we correct that. And if we get number that is between 0 and 360, that is the local hour angle of the star. What I'm saying now, what I'm speaking right now, that is something I'm going to type here on the side. So insert right, and let me just put so I can see where I'm typing temporarily. So this doesn't have to be that large, this needs to be large. So this is with exact hour. This is correction for min and seconds. This is RDR longitude. This is sidereal hour angle of star, and this is local hour angle of star, and this is Greenwich hour angle with exact hour. So let's reduce this. Correction for minutes and seconds, RDR longitude. Let's also put note east plus, west minus, sidereal hour angle star, and okay. I believe this is okay. Greenwich hour angle, correction for all, okay, local hour angle of the star. Okay, I hope this is clear so far. Let's move on to step number symbol, more symbols. Step number 4, insert, close. Correcting the height observed. Correcting the height observed. Now, we have the height of sextant. Let's put it here in table. Let's make a table. So we have height of sextant that we measured. We have our device error. We call it temporarily the error E, index error. We have dip. we have, because we didn't jump in water to measure, so it's plus dip. We have correction for temperature, and we have correction for pressure. Temperature, pressure. And after we apply all of these corrections, once again, I want to note here, in school, you need to split all this. So this plus this is height observed corrected, plus the dip is height observed corrected for the level of horizon, and plus temperature and pressure is height true. So each of these summarizations in between, they have a different name. So height sextant plus index is height observed, plus dip is height observed corrected, and then plus correction of temperature and correction of pressure is height true. We are not in high school. If you are in high school, I will also add that calculation here later on. Once the video is finished, I will complete this textbook with more finesse. But for the purpose of this video, let's keep it simple. Let's keep it the way we do it on the ship. And the way we do it is we just summarize everything in order to get the total value, because this is what we need. We need height true. We do not need this sums in between. So height observed with sextant is far away. So height observed with sextant is this value here. This is HS. HS. Index error, yes, the span of my memory is 0, so index error is, now this is very important, it is minus 0.2, but in order to avoid mistake, we need to write down the full value. So full value is 00 degrees, 0.2 minutes. So it's not 0.2, it's 0 degrees, 0.2 minutes. Now the temperature, pressure, and dip is what we need to get from the table. So that means we need to take table of corrections. Table of corrections. And let's go back to the table. Let's see, do I have my PDF on? Yes. Okay. So we have page for sun. That's not what we need. We are not observing sun. We didn't observe sun. And the last page is for stars and planets. So the top row is height of eye of observer, and we need 16. And on the left we need 30. So let me see how can I get 16 and 30 on the same page? This will work. This will work. Let's take a screenshot of this. Come on. Okay, back to Word. Here we are. Okay, so we have height of sextant 30. Height of eye was 16, I hope. Let's go back a little. Yes, it was. No, it wasn't. Where is height of eye? 16. Okay. Height of eye is 16. Let's cheat. Let's copy this and paste it here. Come on. Come on. Paste. And let's look. We need 30 because our height is 30. Let's spread this all the way up to here, and I need one more. And this one is going to be like this. So 16. So 16 from the top, and where these two boxes intersect, come on, be nice. It's minus 8.8. Every value in this table is in minutes, so that is, let's cheat a little, copy, paste, 8.8 minutes negative. So all the values here are negative. So the correction for 16 meters of height of the eye and 30 degrees height measured with sextant is 8.8. Now, because we do not have technically 30 degrees, we have 30 degrees and 17 minutes, that's almost a half. We should interpolate between 30 and 31, but only if the number between upper one and lower one is higher than 2 minutes of difference, or 0.2 minutes of difference, because we are not going to second decimal value behind the decimal point. So we have minus 8.8 that belongs to 30, and we have minus 8.7 that belongs to 31. Because of that, we are using the result is 8.8. Now try to follow here. If the value for height observed with sextant for 30 degrees was 8.8, so 8.8, and the value for 31 degree is 8.6, stay with me here, 8.6, and I have 30 degrees and 30 minutes, so in between 30 and 31, I can calculate in my head what is the middle between 8.8 and 8.6. So the middle between 8.8 and 8.6 is 8.7. And then if the height is 30 degrees 14 minutes, I would take 30, value that belongs to 30, and if my height is 30 degrees 46 minutes, I would take value that belongs to 31. So it is visual interpolation. You don't need to have to calculate anything. I hope you know the middle between two numbers. But in our case, we have 8.8 and 8.7. So in this situation, if we have any number between 30 and 31, we just take the closer one, because we are not doing this. We are not doing 85. We are not doing the second digit behind the decimal point. So it's either 8.8 or 8.7. If our height was 30 degrees 37.9, we would not pick the value for 30, we would pick value for 31, and we would put 8.7. So because 30 degrees 40 minutes is closer to 31 than it is to 30 degrees. And that is how you use the data from this table. You interpolate visually, just visually, or if you want to, if you need to calculate the middle between, for example, 8.8 and 8.6, the way to find middle is summarize those two numbers and divide them by 2. So that is how you get middle between two numbers. Summarize them and divide by 2. And you would get 8.7. Okay, so let's go to temperature and pressure table. Let me see. I should have it open. Temperature and pressure. Let me show you what I'm doing. So temperature and pressure. So can I take? Okay, I should take a screenshot of this, so I can use it in the textbook. Where's the mouse? Come on, mouse. Okay, let's make it smaller, or make it like this, so we have everything. And let's copy that into Word. Let's go back to Word file. Oh boy, oh boy. So, Word file. Let's copy these one. We can use them here as well. So our height is 30 degrees, so that makes it here. So we find the column on the top. These are the heights or altitudes measured with sextant. So our height is 30, so that means we are between 22 and 30, so we are here. Refraction is 2, and now the temperature is 16, so that means our first correction is 0. So correction for temperature is 0, and for the pressure, oh, I don't remember how much was the pressure. Let's go back. back. The pressure was 980 hectopascals. 980 hectopascals. So let's take this one, copy. Come on, B. So the temperature is here. So this is correction for temperature, and for pressure is 980 negative 01. So the pressure is negative 01 minute. So let me cheat again by copying this. Copy, paste, 0.10. So 0.1 minute. And this is 0. So let's put, oh, okay, let's keep it 0. And let's do the calculator thing. You see my calculator, so let's put 30, 17.9 minus 0 degrees, 0.2 minus 0 degrees, 8.8 and minus 0 degrees, 0.1. And the Houston says it's 30 degrees, 08.8 minutes. Now, how do I know it's 0.8 when the calculator is showing 48? Because 48 seconds divided by 6 is 8. So that is the number I put, because we do not use seconds. We have seconds in time, but not seconds in angle. And that is how I got my height true. I have a message. Let's say, is anybody panicking? New perfect. Okay, I have a new job. I also work as a designer as well, so you have links for my design services in the description below. So if you need any kind of graphic design or similar, you can contact me as well for that. I use the funding I get from my graphic design work to fund this project of maritime science that I'm doing. So let's continue. So we have height true. That is step 4, correcting the height observed to get height true. Okay, so that's step 4. And later on, do I have a columns here? I have columns here, so I will type here everything that I said. Insert right. Okay. So this is, maybe I should do it now. Come on. Go. Height measured with sextant. What is this? Device error or sextant error? Sextant error. Permanent error. Dip, horizon dip, and temperature correction and pressure correction. And this is height true. Perfect. Later on I will add more meat to this explanation, but so far I hope it's come on, look nice, be aligned with everything. Step 5. Okay, the notorious step 5. Symbol, more symbols. Number 5. Now let's put 6, so we have that here as well for the future. And let's go to another page. Step 5, calculating. Yeah, the font, come on, font Arial. Calculating height calculated. So what is height calculated? Come on, Arial. am I typing? Height oh my god, I can't spell calculated is height where the star is supposed to be if we are actually at DR position. So this height here that we get here, height true, is the actual height of that star from our true position. But we do not know the coordinates of this position. What we do know is close your eyes, pick something on Earth, whatever, and you know the coordinates of that imaginary DR position. And now by using the data for that imaginary position, star supposes, no, I like the way it is. Oh, X. Where was I? So I'm going to calculate, we are going to calculate where the star is supposed to be for if we are on that DR position. Now the difference between the value we got in here in 5, step number 5, and step number 4 is going to be our error. So you say, oh, I'm in Africa, and you are actually in America, and the celestial navigation is going to tell you, yes, this is where you believe you are. That's very nice, but because of the height difference, this is the height you measured, and this is the height that's supposed to be, and the difference between those two heights is the nautical miles of your error. So you are not here, you are by this much in that direction. So the first thing that we need is we need to find our error in nautical miles, and to get that we need to calculate the height for our DR position. So where the Elliot's supposed to be, if so sin, now we are entering the trigonometry function, and sin is small. So we have a celestial triangle that has 3 sides. One side is declination, one side is latitude, and one side is height. Because we are looking for height, that means the left over sides are latitude and declination, and between the sines and cosine you always have plus. You do not have multiplications between sines and cosines, never. It's always minus or plus. So in this case it's plus. And then we have cosine of both sides, so cosine of lat times cosine of declination of that star, and cosine of the angle that is opposite to the side of the triangle that we are looking. And the opposite side to height calculated, opposite angle, is local hour angle. And because it's a star, that means the star. So let's go back here and copy this. And if you are just learning, and if you are just starting to do this for the first time, what I recommend is put the numbers in before you start calculating, in order to avoid confusion what goes where and what is what. So sine of latitude, and for that we have to go way back to the start of the task, and the latitude is this, and keep in mind it's north, so north is positive. If it was south, I would have to put negative sign in front. So go back, so sine of latitude times sine of declination. Declination of Elliot was where it was the declination, it's here. It's also north, so it's positive, so we are keeping it positive. If it was south, we would put it as negative, plus, now I'm going to cheat because it's the same two numbers. The only thing that is different, it's cosine, and times of cosine of LHA, and LHA is this number here. Copy. Oh, I went too far. Cosine of LHA, and let's get the result. Equals, and let's, do you see my calculator? You see my calculator. So let's start. This is natural display. So if your calculator has this label on the top, natural display, so that means what you see on the paper is what you write on the let me see just a moment. Okay, y is okay. I'm trying to see, can you see my mouse? Yeah, you see my mouse, okay. So the way you see the formula here is the way you type it in. So if the calculator has natural display mark somewhere on him or on the box when you purchase it, that means the same way you see the formula on paper is the same way you type it in the calculator as well. So sine of, and also look, the calculator I have, when I press sine, it automatically opens a bracket. So that means I have to close the bracket after I press sine or cosine or any trigonometry function. If you have calculator that when you open or when you click sine doesn't open the bracket, that means you do not have to close it for him. In my case, I have to close it for him because he's opening it. So 25 degrees 39.2 minutes and close the bracket. Now if the value of latitude was south, this is where I put the negative sign, so inside the bracket. So inside the bracket, but because it's north, I keep it positive. Let's go out times sine of 55 degrees 54.9 minutes, close the bracket, plus cosine of 25 degrees 39.2 minutes, close the bracket, times cosine of where were we, 54.9 times cosine of 73 degrees 16.2 and press equal. This is a trigonometry function, so that means there is no rounding up. We need everything. 503974079. Now what we need is invert this. We need to get, let's put -1, and where's the this one. So we need to invert this. This is the sine of height. We need height calculated. We need the value of height calculated. Now in order to revert this back to angle, we need to activate the secondary function of the sine button. So the secondary function is here on the top of the button, and in order to do that we need second function. So shift sine equals and press ds or degrees minutes seconds to get the value in degrees. So it's 30 degrees 15 point, and 48 divided with 8 is how much? 8. And that is how you get height calculated. Calculating, let's give me area. Calculating, come on, CA. Calculating distance error, and distance error has a label. Do we have delta? Come on, give me a delta. Yes, delta. Insert delta H. So the distance error is table 4. I don't need more than 4. Is height true minus height calculated. I don't need, it's not bulletin, and that is delta H. Let's copy that. Let's do the left part and let's do this. Height true, bottom border, So height through was where was it? 30 degrees, 8.8, copy. Height calculated is 30 degrees, 15. So minus, no, we have to go back. So 30 degrees, 8.8 minutes minus answer is, what is this? 7. Exactly 7. Why am I calculating this? Minus 0 degrees, 7.0 minutes. And because 1 minute of height is measured on the same arc as latitude, and 1 minute of latitude is 1 nautical mile. 1 minute of height error is 1 nautical mile error. Okay, so in this case we got that between our assumed position and our true position the error is 7 nautical miles. Possible true position is 7 nautical miles, 7 minutes. Now the distance from true position and assumed position means nothing to me. If I tell you to meet me 200 meters away from the bus station, what that gives you is a circle. So anywhere in 200 meters away from the bus station could be my position. What I need is bearing. What I need is azimuth. So step number 7 is to calculate the actual direction of this error. So direction of the error of 7 nautical miles. And that is step number, where I'm missing, step number 7. Is it 7? Yes. So azimuth, calculating azimuth of star. Okay, so that's step number 7. So azimuth is the angle of the celestial triangle. And formula for, let's do the table. Let's merge home, layout, merge and center. So cosine of azimuth, let's find the sign for azimuth symbol. Azimuth is this one, small Greek letter omega, and it's calculated. And let's go back here. So azimuth is sine of the side that is opposite to azimuth, and opposite to azimuth is declination. Declination is opposite to azimuth, minus sine of the remaining two sides. So this is easy. We have latitude and we have sine of height calculated, and I'm going to copy this because they are repeating on the bottom, but they just change into cosine. So cosine. So this is the formula to get angle. Okay, and no border, and this needs to have bottom border. Okay, so this is the formula to get azimuth. Why do I have to get azimuth calculated? We do not put true here, we put calculated because we are looking for azimuth calculated, where the star is supposed to be, not where the star actually is. So that's why we are using height calculated. And let me copy this. Once again, if this is your first time using this formula, I recommend that you actually put the values here. So declination is this one. Declination is this one. Latitude is this one. Copy. So we have it here, and here. And height calculated is this one. So height calculated, and height calculated, and let's spread this so we can see the numbers and center it. Okay. Why are you? Okay, we have some extra spaces here. Okay, so this is what we have. Let's copy outside the table. So if you have this button on your calculator, you can use it. It will give you this function that you can type everything what is on top and everything on the bottom separately. So let's start typing. Sinus of 55 degrees, 54.9 minutes, minus sine of 25 degree, 39.2 minutes, times sine of 30 degrees, 15.8. 15.8. Now look what I'm going to do right now. I'm going to deliberately tell the calculator, deliberately, but in real life it would be my mistake. I would say sine, calculate me the sine of 30 degrees and 50.8 bananas. Because he doesn't know what this is, because I didn't tell him. So I'm going to 50.8 bananas, and I'm just going to close the bracket. So this is something that can happen to me by mistake. I forget to put this as a degree and this are minutes. And let's just continue. Let's go down and put cosine of 25 degrees, 39.2 minutes, close the bracket, times cosine of 30 degrees, 15.8 minutes, close the bracket. And look what's going to happen when I press equal. Syntax error. Syntax error. So it's telling me that I made an error somewhere. According to his logic, something is wrong. And I have these two arrows and they are go to. So if I press one of these two, it's going to blink under the location he believes something is wrong. So if I do this, you see, he's blinking. Marina, you told me 30 degrees, that's fine, but what is 15.8? Is it bananas, is it kiwis, or is it minutes? And if I tell him now it's actually minutes, he says, okay, thank you, this is the result you need, and that is 0.7835065582. And once again, I need to convert this. I'm going to cheat and copy. I need to convert this into cosine reverted to get azimuth calculated. Azimuth calculated. So shift cosine equals 38.4. 38.4. This is an angle. Because this is an angle, we keep it in degrees and we keep it one decimal point, one number after the decimal point. Because you cannot draw minutes with the nautical triangle. So when it comes to degrees, like course, bearing, azimuth, bow angle, aspect, we keep that in full degrees. We do not convert that into minutes. So if the result was this, if the calculator gave me this, I would press DMS button, degrees, minutes, seconds, to convert it to full degree. So azimuth calculated is 38.4, but we have a rule. Let me copy the rule for you. Let me see the rules. Come on, rules. Let me screenshot the rules for you. We have rules. So if LHA of the star is greater than 180 degrees, then azimuth true is equal to azimuth calculated. But if LHA of the star is under than 180, it's under 180. Okay, I have to correct this. This is not under, then it's under 180 degrees. Then we need to get azimuth true by subtracting calculated from 360. So azimuth true, copy, azimuth true is, let's see how much is the LHA. So LHA is under 180, so that means azimuth has to be over 180 because azimuth and LHA are measured in different directions. So that means 360 degrees minus 38.4 degree equals, and let's 360 minus answer is 321.6, 321.6 degree. And that is my true azimuth. That is the actual azimuth of my error. That is the direction in which I made a mistake by 7 nautical miles. Okay. And now after this is finished, where is it? After this is finished, let me check the results. Yes, everything is okay. 321.6. Yes, everything is okay. After I have this, the step 8 would be symbol, more symbols, numpal, step 8 would be plotting the data on white chart. Plotting the data on white chart. I need to make this better. And that is the procedure for known star. Now, comparing to what we did yesterday and what I did today, I would like your feedback. If anybody is still here listening, or it's just me talking to myself. Is this okay? Can you follow this? Is this clear? Now this document I'm preparing, once everything is finished, it will be available on my webpage for purchase. Also, if you are candidate in one of my training centers, you will be given this as a part of the preparation for the course. When you signed up for the course, you will receive this document or similar document. I believe I will make a couple of them different so I can track which one is which. Hi Matthew, you're still here. Is this okay? Can you follow this? Is the process clear what we are doing here? This is just for the known star. Now we're going to go for the known planet, but everything from this point is going to be easier because the star has the biggest amount of things to do. Everything else is just variation, just different tables, different values read, but the process is more or less same. Okay. Now, Matthew, I know you have schedule, I know you have things to do, but I would like to continue with the planet for this video as well. So if you have to leave, you can leave, but I will continue with planet and then I'm going to stop because I want to have 2 of those in one video. So I have star sold, and then I'm not just going to copy paste everything and make a duplicate for planet. So let's copy everything up to here, copy, okay. So this was the procedure for known star. So in case you have 2 stars, 3 stars, 10 stars, doesn't matter. You just repeat all the steps. So step 1, you find the correct UT time and date. Step 2, find the correct date page in Almanac. Step 3 is calculate local hour angle of the star. local hour angle of the star. Step 4 is correct the height observed to get height true. And once you have that, calculate the height calculated and calculate distance error and calculate azimuth of the star. And let me just put true azimuth of the star. I keep forgetting of the star. And once you have those 7 steps solved, then you plot the data on Y chart. Now the only difference is if you have one star, you solve everything up to step 7, and then you plot the data on the Y chart, one Y chart, and then when you do the second or third star, you plot the different data from the different star, but on the same white chart. You do not make a new Y chart for each individual star if they are part of the same task. So you do step 8 on the same Y chart for all the stars in the task. So let's see how the procedure is different in case we have planet. So I just copy paste everything, so it's easy because I'm just going to change the numbers. Now we already know what chronometer is, so I can delete this delete table. Also we know what sextant is, so we don't need that here. So observer is observing, let me get the data, known planet. In this case we're going to have planet, and it's going to be the specific one, Mars. The date is the same, the position is the same, and everything is the same except the time of observation for Mars. So we observed Mars at chronometer time 23, 59, 58, and the height of observed with sextant of Mars is 8 degrees 18.9. So the first step is to get the correct UT time, so that is easy. We already know how to do this. The error is the same because it's the same device, same ship, same everything. So the time is 19 and 58. So 23, 58, 19 is the correct time. The date, because we didn't cross the midnight, it's still the same. And now we need to make page break. And now we are looking for 23, but we need to spread this because we are looking for Mars data. And for Mars, we have, it's no longer 57, it's 58, 19. So we need to read, so the purple is, we need to read with full hour from UT time, we read value of GHA for Mars. So Mars is a planet, and GHA of Mars, let me see, do I have, Mars is stars, so let me get Mars. Okay, copy. So the index has to be sign of a planet. Okay, so it's Mars. Fancy Mars, but it's Mars. So from the Almanac, under 23, under date 31, we have 137 degrees, 54.6 minutes. So that is Greenwich hour angle of planet Mars, not this one. And now also, while we are here on the same page, same hour, we can read out the declination of planet Mars. And declination of planet Mars is, copy, declination of planet Mars is, what is it? Now, When it comes to printing of Almanac, usually they save ink by not printing the same number all over. So here you have number 2 and then you don't have it. And then once again you have number 2 and then you don't have it. So that means it's number 2 all the way here, but they do not print it. So don't just put, it's not 43.9, it's actually 2 degrees 43.9 south. So this is just how they save ink. One common thing people make mistake is when they are printing, they thinking if I make the book on 20 pages instead of 30 pages, I'm saving, and they are using the same font. That is not going to save you. The paper is very cheap. The expensive part when you print something is the ink. So if you want to save money, especially if you have, let's say, a large company, maybe tomorrow you want to open your company and you want to like save $10,000 on printing, is by selecting the correct font. So you have Arial, here I have a font here, I have Arial, and I also have bolded version and I have a thinner version, so you have Arial narrow. Now the difference between printing in this one is $10,000 in ink. So you have same amount of pages, same amount of text physically printed on the page, but if you select font that is thinner, you will save on ink, and because the ink is what is expensive. So keep mind on that. So that is one thing that they do here. They actually physically do not print the number that is constantly repeating to save the ink, because ink is expensive. They can print Almanac instead of 200 pages on 400 pages and still keep the cost low. But if those 400 pages have thicker letters or more amount of numbers printed, they will increase the cost by the cost of ink. So that is the reason why they do not print all the numbers, why we do not have 2, 2, 2, 2, 2 in every row. We just have the number 2 on top. But don't forget it. So it is 02 degrees, 43.9 minutes south. Note how the declination is changing in next hour. So that is what we need to look as well when we are looking at declination of the planet. We need to note what is happening to declination in the next hour. So in our case, declination of Mars is 43.9 south. In the next hour, it's 44.6 south. So that means it's going further deep into the south. So that means declination in next hour is increasing towards south, meaning the correction for declination is also south. Now we do not know what is meaning. Learn how to type. Okay. So declination correction is south. We do not know the value of the correction, but we know it is south, because if this is at 23 o'clock and we need to calculate declination at 23:58:19, it's going to move towards the south, because in next hour it's moving towards the south. So how do we get correction for declination? So let's put the table for calculation here. We have declination of Mars, and we're still going to have declination of Mars on the end, just with the correction applied. Now the correction depends on the D value, and let's make some space here. Now D value is not the correction. D value is how much declination is changing between 1 hour and next hour on average during those 3 days. And the location where we have the D value is, I have to switch back to PDF. Let's get the PDF and let's get the Almanac. Where is Almanac? Okay. So we have a page for Mars, 31st of August, and then we scroll to the bottom of the page, on the bottom of the page here, and let me take a screenshot of this. Okay, let's copy that into Word. So on the bottom of the column, we have this. Let's go back to Word. We have two values. We have V value and D value. D value is 1.34. No, this is for, sorry, this is for Venus. The first one is Venus, the second one is Mars. So the second one is, let me confirm, yeah, second one is Mars. So I'm looking at the second one here. Let's get the mark so I know what I'm doing. So let's put it here, V or D. So 0.7. So 0.7 is the D value. That is how much declination is changing on average between 1 hour and the next hour in those 3 dates of that page. So declination is 0.2 degrees, 43.9 minutes south. Because it's south, instead of south, I don't type south, I put minus in front, and it's not bulletin, it's minus. And the correction, I don't know what the correction is, but I know it is south. I know it is negative. And later on, when I reach that part, I will actually get the correction and I will type it here. So this is what we actually do in celestial navigation. We do not calculate everything the moment when we are typing. We just make the preparation. We make this pattern like this. You write this down. And then later on, when you are on the correct page to extract that data, you typed in the data. So basically, what we do is we type this, we type, where is it? We type this, we type everything. We make all these patterns and then we fill them in with data. And once we fill all the data in, then we do the calculations. So we calculate after we filled everything that needs to be filled in. So that is declination, and this is what we read from this page here, the front page. And there is nothing else here that we need for Mars. We have Greenwich hour angle, we have declination, and we have on the bottom, we have the V value and D value. D value is for declination, V value is for Greenwich hour angle. So the purple one is 58.19, so let's get 58.19 here. So 57 is not valid anymore, I don't need that. And the minute is 58 under planets. So we are focusing on the planets and column 19-second values. So let me get increment and corrections. Increment and corrections, and minute 58. Minute 58. New. Oh, perfect. Okay, so I have what the color I used before. What did I use? What did I use? It's going to be orange. Yeah, it's going to be orange. Let's copy that. If you are getting seasick when the screen is moving too fast, then you are not going to survive on the ship, so be careful. So I'm deliberately changing the screen too fast, so it's a test. Are you getting motion sickness? So 58 minute, 19 second, and for the planet correction is 14 degrees, 34.8 minutes. Because Mars is planet, I'm reading the correction for planets. Before we had star and we enter Aries for star. So 58.19. Is it 58.19? Did I made a mistake with UT? No, it's 58.19 on that same date. Now, there is something interesting here under 58. I told you we have this table here, and it's separated from this table here, we have another table on the side also belonging to this minute, 58 minute. So now we need to extract the correction for declination. Now the D value is what we enter here. So the seconds are no longer important. So you completely ignore this part of the table, all these columns, because this is for local hour angle. We do not need this. We are now focusing on this side here, 58 minutes. Seconds are not important, and we enter this side with the D value, and the D value was 0.7. So for 0.7, correction is 0.7. You see here, for 0.7, correction is 0.7. So that is the value I put here. So this is just by coincidence that the D value is the same as correction. So it's not going to be always the same. So keep in mind, it's not this number copied here. You use this number to get the correction. It's not going to be always the same value. It just so happens because we are very close to full hour. 0.7 is how declination is changing in whole hour, 1 hour, and our error is for 58 minutes. That's very close to full hour, so that is why these two numbers are the same. But in reality, if this was 38 minutes, it would not be 0.7. It would be some different value. And now we can get the result. So 9 plus 7 is how much? It's minus 0.2 degrees, 44.6 minutes, and because it's negative, it is south. So if I get negative result tells me that the value is south. Declination is south. So basically what I did now is not good, because this should be here. And this should be deleted, because at this moment, at this stage, I didn't know the value. And now once I'm in this table, I can read the, where's the orange? I don't have orange. I must have orange, yeah. Orange, copy, V, and 0.7. Oh, I'm going to need more colors for this one. So this is the correction for declination. So 0.7 gives me 0.7. And now I have Greenwich hour angle of planet. Let me get the sign for planet. And it's going to end up as local hour angle. So this would be Greenwich hour and planet, and these two can be deleted. We do not need them, or maybe we do need them. Yes, we need them, because it's Mars. So we have a pattern to calculate Greenwich hour angle of planet Mars. So we have Greenwich hour angle at exactly that time, hour, and then we have correction for minutes that we extracted from here, so 1434.8, and that will give us Greenwich hour angle of planet Mars for exactly that hour, minute, and second. And now I need to flip these two. This is going to be here, because this is planet Mars. Planet Mars has its own very unique correction for the V value. The V value is located on the bottom of the column of the planet. Just next to the D, we have the V value, and V value is 1. So the V value goes here, so it's 1.0. So it's not a correction, it's just the value that we used to get the correction. So for 1, under the same minute of UT time, so only minute is important, not a second. Let's copy paste, and for 1 the correction is 1. So for you enter this with V or D, so either V or D to get the correction, and the correction for V value 1 is 1, so 1 minute. So here we have 0 degrees, 1.0 minutes. So 1 minute is the correction. And this is unique LHA correction for planets. Unique LHA correction for planets. So stars do not have this correction, and sun doesn't have. So sun is also a star, so therefore doesn't have this correction. Only planets and moon have this correction. So what was the Greenwich hour angle of Mars? Let's see it here. It was 54.6. So that goes here. The error is 1434.8. Did I type it in? Yes, 14. Copy. 1434.8, and this is going to give me Greenwich hour angle corrected. And longitude is, how much is longitude? I have it here. Copy here, negative west. So once again we have this option where we're going to take everything step by step, or I can copy this, paste it here, and then cheat Greenwich hour angle for exact hour for planet, correction for minutes and seconds, and this is, let's delete this one, layout, delete this row and delete this row because we do not need the sums in between, and let's remove the border, and let's get this into one row. Okay, and put this all on the right side. So the correction is this, this is this, and local hour angle of planet RDR, and delete this so it's not new. Come on, delete everything because this was before. That's it. So we have Greenwich hour angle of planet Mars for the exact hour. We have correction for minutes and seconds. We have a unique LHA correction for planets that we read with V value and UT minute under the increments and corrections tables. And we have longitude of RDR position. And when we do this mathematically on calculator, 137 degrees, 54.6 plus 14, 34.8 plus 0, 1 minute, and minus 72 degrees, 56. It's 79, 079, 34.4 minutes, and go right. That is our local hour angle of planet Mars. So if you have Mars, Jupiter, Saturn, Venus, this is the difference between the procedure for star and for planets. Stars have their own unique SHA and they use Greenwich hour angle of Aries, spring point, while planets, they have their own unique GHA, Greenwich hour angle, but that Greenwich hour angle has a correction, and we can also call that GHA. It doesn't matter, or maybe it's better. It has a unique hour angle correction for planets, and the result is LHA. The same rule applies for everything, for everyone. LHA is measured in arc of 0 to 360. It cannot be less than 0 or greater than 360. And now we have the correction of height. Now because the planet is having the same table as stars, so correction for height of star and planet is the same table, I can use that here. I just need to read the value of, where is the value? That is the beginning. So this is Mars, this is Mars. Height of sextant is 8. So let's copy that. So the 8 is here. Now index error, because we use the same device, is the same. This is going to be different, this is going to be different, and this is going to be different. So let's delete that. So we are looking for height of sextant 8 from the left. So from the left we need 8. And on the top we need 16. And is the height exactly okay? So we have, this is what I was talking about earlier. We have height 818, so that's approximately 8.3. And now we have, for 8 degrees the value is 13.6. So let me write that down. So for 8 degrees I have minus 13.6 minutes correction. And for 9 degrees I have 12.9. So minus 12.9 minutes. I need for 8.3 degrees. That is my height. My height is 8 degrees, 18 minutes. 18 divided with 6 is 3, so that's 0.3. So what that means, I need to find a value that is by percentage of 30%, because between 8 and 9 is 1, so 100%, difference from 13.6. So how to do this? Usually I would do this just by sight. I would not use calculator, but if we want to be precise, what we need to do is 13.6 minus 12.9 is 0.7. So the total distance between the value for 8 and value for 9 is 0.7. I need 30% of that 0.7. So that is, how do we get, usually I do this by head, so I have no idea how to do this by calculator. Let's see, is it by multiplying it by 0.3? Yes, it is. So it's 0.2. So 30%. So 30% of 0.7. That is what we need. Why 30%? Because between 8 and 9 is 1. And we have 0.3. So that means our value is 30% over the value of that we have in table, so value 8. The difference between the two belonging values to 8 and 9 is 0.7, so that means 0.7 is equal to 100% of error between those two values. And I need to know for 30%. How much is this for 30%? And for 30% is 0.2. Like I said, this is not something that I would normally calculate. I would just do this by head. So I have 13.6, I have 12.9. So that means in between is 13.4. That is what I would do. But if you want to calculate, that is how you calculate. You are calculating percentage. How come it's 13.4? Because in between we have minus 13.5, minus 13.4, minus 13.3, so all the way up to 12.9. So for 8.1 and 8.2 it would be 13.5. For 8.3 and 8.4 correction is 13.4. so by 0.2 smaller than what's the value for here. This is just pure mathematics. If you ever go to the store and you want to buy something that on the discount, the way you calculate the discount, is it cheaper if you buy 2 plus 1, or is it cheaper if you buy something that is 35% off? Which one is better option? Which one is better deal for you? So that is basically what we are doing here. There is a mathematical process how to get this precise. Once this video is finished, I'm going to write that down, because I have to admit I have no idea how to do it professionally. I do this by head, because I know how to calculate percentages by head. I don't use calculator. But later on I will do this, I will explain this in the afternoon with calculator, the procedure. But to continue, we need to take the temperature and pressure. So we have that here. We do not need this big, it can be this small. Okay, like this. And for temperature and pressure, our height is 8.3, so it's here. So that means the correction for temperature is -0.1, and for pressure is -0.2. So we have both corrections, -0.1, -0.2. So this one is copy, this one is -1, and this one is -2. So how did we get that? We enter the column for latitudes between 8.3 and 9.5, and we enter from the left with temperature and from the left with pressure, and we read out the value. And we get, after we do all the math, we get how much? So 18.9, 13, so we get 5 point something. We get 5 point, let's copy this. It should be 5.6 or 5.9, -2 is 6, -4 is 2, okay, I need to use calculator. 18.9 minus 0 degree, 0.5. I summarized this one, and this one because together they are 5, and minus 0 degree, 13.4 equals 85, exactly 5. 5.0. So this is negative. This is dip. Okay. This is temperature. This is pressure. Oh, wait. This is Mars. Specific table correction for Mars. I knew I was missing something. So plus Mars correction. And the Mars has its own correction. I'm going to show it in PDF. Let me show you the height correction. Where's the height correction? Table of corrections. Yes. On the bottom, you see here, Mars is unique and it has its own tiny unique correction always. So always second correction for Mars for calculated or measured height is 0.1 positive. So that means I have one more correction here, and it's copy here, positive 0.1. So that means it's 4.9 or 5.1. No, it's 5.1. So that is height true of the planet Mars. So Mars is unique when it comes to height because it has that second small correction, and it's the same for Venus. So Venus and Mars are two planets that have the second correction for height. Saturn and Jupiter, they do not have that. They only have one correction. So we have sextant error, that is depending on our device. We have specific correction for Mars. We have horizon dip. We have temperature correction, and we have pressure correction, air pressure, air temperature. And the end result is height true. And after this, because it's already been 2.5 hours, I will stop with the video. I will make later on, somewhere in the future, I will make timestamps for each of the steps, so it's easier for you to scroll through the video. But the rest of the procedure is the same. So we have step number 5. using this formula to get height calculated of Mars, so it will be different values. Declination will be different, latitude is the same, local hour angle is different, so these numbers need to change. The distance and then azimuth using the formula will be different, but these two steps I believe are quite clear. You have formula and you just type in the data inside. This was important. Step 3, how to calculate local hour angle of planet Mars, of the planet Mars, and how to correct the height observed to get height true for the planet Mars. So that's it for today. We are finished. I will continue working on these two sections of the document, and tomorrow morning 10 o'clock I'm going to do the same thing like this for sun at any moment, sun at noon, and sun at sunrise and sunset. That's the schedule for tomorrow. So the same concept as today. I will work on my document and I will show you the step by step of calculation. And then after I'm finished with the document, what I'm going to do is I'm going to copy everything, so twice, and I'm going to delete the numbers, like here I'm going to delete these numbers, and I'm going to extract the patterns, these patterns, and you can use this pattern on the exam. So no matter where you are, where you're attending the exam, you can use these patterns for the exam. So you would have the title, Celestial Navigation Known Star, and then you will have pattern for time, UT, you will have pattern for LHA, and you will have pattern for height, and you will have these two formulas for height calculated and azimuth with the rules on one page ready for you to use on the exam or for practice when you are practicing celestial navigation. So that is something for me in the future that I will do. Like I said, this document, once it's finished, it's going to be available. Okay, thank you, Matthew. Thank you everybody who's listening here as well. Thank you everybody who's watching in the future. Keep in mind, this document, once it's finished, I hope I will finish it completely by the end of the next week. It will be available on my website for purchase. If you are a candidate in a training center where I work as instructor, you will be given this document as a part of the course, depending which course you took. So not every course, but for some courses you will get this document in advance. So if you're attending Yacht Master courses, boat leader course, and you know this, please ask for this document in advance, not on the day of the course, because on the day of the course is already too late. You need to know this before you come to the course, especially the part of you using the calculator as well. The Almanac I'm using for the preparation book and textbook is available on my site. So it's here with my publisher. You can purchase it and it has worldwide shipping. It's Nautical Almanac for Education, so it's always valid. It's not going to be obsolete next year. It's always going to be functional, and it's always going to be good for practice in school or for somebody who is learning celestial navigation. Thank you very much. And if you have any questions regarding this or regarding anything else that is connected to celestial navigation, any navigation or ship stability or something regarding maritime industry, let me know. Have a nice day and talk to you tomorrow.